So, good morning everyone. First of all, I would like to thank the organizers for inviting me here to this very nice workshop. It's just the first morning and I already got involved in several very enjoyable discussions. There is actually one correction. I'm in the middle of moving from Stanford University to Switzerland, where I will be affiliated with Paul Scherrer Institute and with the University of Zurich. And my talk is in the context of topological band theory, so it's related to problems like topological insulators and one semi-metals. And more precisely, we show that even in the absence of interactions between the particles, there are some aspects of topological band theory which really require definition of some non-Abelian topological charge to be explained. We first spotted this in this very recently published science paper, which was done in collaboration with Chuan Shengpu and Alexei Solyanov. And among the predictions which we make, we say that it is in principle possible to break band nodes non-trivially inside the momentum space. So I'm not going to explain what is the meaning of the colors in this diagram, but to see that you have some point nodes, and as you tune the Hamiltonian parameters as a function of time, they are braided. And if the band nodes are able to annihilate at an early time, you would see that after the braiding they would not be able to annihilate anymore. And we investigated some aspects of this braiding in two follow-up works, one with Apurv Tiwari and another one with Robert Jan Schlager and Adrian Bohon. Now, to explain how this works, I will actually start with a small mathematical trick, which most of you know, and it is about studying rotations in 3 dimensions. And it turns out that this is really relevant for the physics that I want to explain. So it's known as the Deluxe belt trick. And I will do the experiment. So the question is, what happens when you rotate an object by 2 pi? I borrowed this book from my hotel room. It's called The Teaching of Buddha. That's what was said. So now the thing is that if you take an object, so solid 3-dimensional object, and you rotate it by any axis around by angle 2 pi, then in the end it returns to its original state. So 2 pi rotation looks like a do-nothing transformation. However, if you take a belt, and I have here this 2-color belt, which has dark one side and bright other side, then if I have one end fixed and I twist the other end by 2 pi, so I'm doing one twist, that's pi, and another twist, that's 2 pi, then in the end you see that actually there is some deformation. There are these 2 twists along the way. So the 2 pi rotation of one endpoint of the belt looks like something non-trivial. Now the difference between the belt and the book is that the book has no memory, but the belt keeps some track of the history. As you move from the one endpoint of the belt to the other endpoint of the belt, you keep some memory of the fact that the belt has been rotated. Now, the funny thing is what happens when you rotate the objects by 4 pi. 4 pi means doing the complete 2 pi rotation 2 times. Now, when I do it with this book, it becomes a very boring exercise in doing nothing with the book. Now, when you do it with the belt, it also looks like a very boring exercise in twisting the belt. So let me do it. So I do first 2 twists, so there's a 2 pi rotation, and now I do 2 more twists, so now I have a 4 pi rotation. And now you see that the belt is twisted because it keeps memory of being twisted. However, the funny thing is that this belt is not really twisted. Now I can disentangle this by not actually rotating the endpoints, just by moving them around. And the trick is actually something like that. So you see, when I take it back, it's twisted. When I move it around, it gets untwisted. So 2 pi rotation really was non-trivial for the belt, but 4 pi rotation really becomes trivial. It doesn't work with the 2 pi rotation. I can also show you what happens when I start the 2 pi rotation and I try to do the same trick. So you see there are 2 twists now. When I do the same trick, I carry the endpoints around, then there are still 2 twists. So this is a famous trick due to Dirac, which was explaining the spin representation of rotations in 3 spatial dimensions, and it's actually very relevant for the physics that I want to clarify. Now, if I were a professional magician, I would not tell you secrets behind my tricks, but we are scientists, so there is a lot of pressure to make science open access. So the trick goes as follows. This is a belt. If you want to describe the configuration of the belt, then what you can do is that you assign to each point on the belt some orthonormal frame where these 3 arrows, the blue, the red, and the green, define really the local orientation of the belt. So the red is along the belt, the blue is perpendicular to the face, and the green is the remaining direction. And now, as you move along the belt, you will see that this frame is being rotated. So you can define the configuration of the belt by saying what kind of rotation you have to perform as you move along. In this trick with the belt that I showed you, there was additional constraint, which was that when you get to the end point, then I did a 2-pi rotation and the 4-pi rotation. The orientation of the belt at the two ending points, the start and the end, is the same. So the total rotation is going to be trivial. Now, to explain what's happening, you need to understand the topology of this manifold of rotations, the SO3. And it turns out that this manifold can be encoded very handily in this way. Any rotation can be understood as rotation by some angle which is at most pi. If you have rotation by an angle which is more than pi, then you can imagine that you are rotating around the opposite axis in opposite direction by angle less than pi. And also, every rotation is characterized by this angle of rotation. So now, the axis of rotation, the angle, you will do the following mapping. This rotation will be mapped to a point in three-dimensional space, at position alpha, the angle of rotation, times the unit vector n, which will be some point in three-dimensional space. And all of this together constitutes some three-dimensional ball. So SO3 is something like a ball with a funny boundary condition that rotating by pi in one direction and rotating by pi around the opposite direction is really the same geometric transformation. So you have to identify these antipodal points on this ball. So this is how you can understand the space of rotations. Now, when I did the trick with the belt and I did only the 2-pi rotation, then the deformation which I did was the following. I was rotating by, well, around some fixed axis, so this is a straight line, by ever increasing angle. So first I did the pi rotation and then I did another pi rotation. So I actually formed this closed path inside SO3. And it turns out that whatever how you try, this path is non-contractible. It is not possible to continuously shrink this path to a point. You can try to rotate this crazily around, but you will not be able to disentangle this because you see that this path crosses this ball at two antipodal points. So these green dots are always going to be opposite to each other. However, if you rotate by 4 pi, that's what I try to animate here, then I intentionally do the second 2-pi rotation around a slightly different axis, then it turns out that this actually is a contractible path inside the space of these rotations. You can imagine that you are going to pull this place where this blue arrow is crossing the boundary of the ball slightly to the left, and simultaneously you are pushing this part to the right. And when you do so, then actually the path deforms into something which looks like this. And here it should become clear that this really is contractible. You can pull this arc completely over, and then you can shrink everything to the point. And this is what I did. This is what I did with the 4-pi rotation on the belt. I unbound it in this way. Now, what is actually even more relevant for the physics that I will explain in a moment is to study rotations by pi rather than 2 pi. And again, I can study rotation by pi around two perpendicular axes. And with the book, it becomes a boring exercise. You can rotate it by pi around the horizontal axis and by pi around the vertical axis, and you get some orientation. Now, instead, I could rotate the book first around the vertical axis, then around the horizontal axis. And you should see, I mean, the camera should see, that the final orientation of the book is the same. So for rotations as geometric transformations, the pi rotations commute. However, with the belt, it's not really so. I can try to do the same thing with the belt now. So again, I start with the belt. And I'm going to do these 2 pi rotations. So let's say that I will have a rotation in this direction. That's the twist. And I will have a rotation in this direction, which will correspond to some folding of the belt. So let's see. I first twist it by rotating vertically. That produces one twist, that's the pi rotation. Now I am going to rotate by pi by folding left to right. I obtain something like this. Now I undo the first vertical rotation and I undo the folding. And as a result, you see that the result is tangled. You have a 2 pi rotations. There are 2 twists along the way. So it's a not difficult trick. You can do it at home. So geometrically, these transformations commute. But if you keep the memory, if you do it with the belt, they do not commute. And actually, if you calculate this commutator of the 2 pi rotations, you will find that the result is a 2 pi rotation. And 2 pi rotation, as I told you, is something non-trivial, something that you cannot get rid of if you keep the memory along the way. Now, in quantum mechanical systems, you very often do keep the memory of the path. That's the Berry phase. As you go around a closed path, you come back and you keep some memory. That's the phase that you obtain. So this is going to be important. Now, how does this matter for band structures? Now I finally get to the physics. So let's say that you study block Hamiltonians, so I will call them H as a function of K, which are not general Hermitian matrices, but they are real symmetric matrices. It turns out that this is guaranteed to happen if the system has the following symmetry. Some symmetry which is anti-unitary, something that communes with the Hamiltonian, and something that squares to +1. So there are three conditions. If you have these three conditions, then you can show that the block Hamiltonian is real symmetric. And this is not so much fine-tuning as it seems. It turns out that in 2 dimensions, composition of a pi rotation with time reversal has this property. And in 3 dimensions, composition of inversion with time reversal has that property. So these are very generic symmetries. So if these conditions are fulfilled, then of course you can, real Hamiltonian, it means that you can gauge the eigenstates of the Hamiltonian to be real. It's always possible to gauge them like this. There is still going to be a sign ambiguity, some sign redundancy. In usual complex quantum mechanics, you can multiply your state by some phase, e to I phi, and it's still the same phase. Now in the real case, you can multiply the state by -1, which kind of flips the vector, and it's still the same state. So there is some redundancy that we need to keep in mind. The eigenstates are orthogonal to each other. So if you collect all the eigenstates of the Hamiltonian, they spend something that mathematicians call a frame. So for example, for some 3-band Hamiltonian, you could have these 3 frames forming, the 3 eigenstates forming this frame, where 1, 2, and 3 are the 3 eigenstates. But because of the redundancy, you can flip the orientation of any of these, and they are still going to be the eigen frame of the Hamiltonian. So for example, if you rotate by pi around any of these directions, you see always a pair of states obtain the minus sign. So these are still the eigenstates of the original Hamiltonian. So these are 4 different ways of encoding the eigenstates of a 3-band real symmetric Hamiltonian. Now, we are almost there in seeing how the Dirac-Bell trick plays into something non-commutative inside the momentum space. But to really get there, I will have one more intermediate step. Let me assume that I study this very simple thing. I have a 2-band model decomposed using Pauli matrices in this way. And you see that if you set kx and ky to be 0, you have a node, there is a band degeneracy. And I will take a path going around the node, and I'm going to look for the 2 eigenstates of this 2-band Hamiltonian. And you might find that, okay, here in this position they could be encoded by these right pointing and upward pointing arrows. But now, as you go around the trajectory and you keep the eigenstates real, and you want the eigenframe to rotate continuously, then you will see that as you complete your trip around the band node, the eigenframe is rotated by pi. So this is the same eigenstate. They differ from the original one just by this flipping, the minus sign, some kind of real gauge transformation. But actually, if you really want to have these states continuous and real along the way, you will get this, this discontinuity, this pi rotation. So you see that if there is a band degeneracy in these real symmetric Hamiltonians, it is associated with the pi rotation of the eigenframe. And the most interesting thing happens when you go to 3-band models. So here I have some example 3-band model. You see bands 1, 2, 3, and you see that there are some band nodes in the lower band gap, and there are some band degeneracies in the upper band gap. And now, if you consider the eigenframe in the vicinity of this node formed by the lower 2 bands, then what you see is that the state describing this uppermost band, number 3, is basically constant. It doesn't do anything. But if you follow the discussion from the previous slide, you would find that states 1 and 2 will perform a pi rotation. On the other hand, if you take a small loop going around the node up here between the upper 2 bands, then you see that the bottom band, number 1, doesn't do anything. It can be basically constant, while bands 2 and 3 will perform a non-trivial pi rotation. And what you see is 2 pi rotations about perpendicular axes. And it's quantum mechanics, so we'll keep some memory. So as a consequence, there will be some non-commutative properties, similar to the trick that I just played with the Dirac-Bell. So we are back to this example that I started with. To really demonstrate that this works, I can just show you some data for a model. I'm not going to showing you the Hamiltonian behind this model, but there is a 3-band model. These red dots correspond to 2 band nodes in one band gap. These blue nodes correspond to band node in the upper band gap. You can ignore the orange background for now. You see that I'm encircling these 2 red band nodes in one band gap using 2 paths, the brown one and the pink one. And because of the blue node in between, you cannot deform one into the other one without doing something discontinuous. And now you can calculate what is the total frame rotation angle that you accumulate on one path versus the other path. And you will find that on one path, in the brown one, the pi rotations associated with the red nodes add up together, so pi plus pi is 2 pi. While on this pink path, the pi rotations cancel each other, pi minus pi is 0. And as a consequence, if you try to bring these bent nodes together inside the brown path, they will not be able to annihilate. The 2 pi rotation is really an obstruction. On the other hand, if you bring these two red nodes together inside this magenta path, on the other side of the blue node, then there is no topological obstruction. The total rotation is trivial. So as a consequence, you see that the fate, like what is happening with these bent nodes when they collide, depends on the trajectory that you use to bring them together. So that's the braiding aspect of this. Now, this really is beyond the usual tenfold way description of topological insulators and superconductors. In tenfold way, when you look at the symmetry class, it tells you that these band nodes carry just a Z2 charge, which is the quantization of Berry phase to 0 versus pi. Yeah, you see that the total Berry phase in this brown path is trivial, so you would expect them to annihilate. So this it really goes beyond tenfold way in some way. It goes beyond the tenfold way in the following way. So it's really the interaction between two species of band nodes which is important. In the usual tenfold way, what you do is that you say that some of these bands, you see this is dispersion, energy versus momentum, some of these bands will be projected as occupied to energy minus 1, while the other bands, which we call unoccupied, will be projected to some energy plus 1. And in tenfold way, you only keep about preserving this one band gap in the middle. So you see that these red nodes, which supposedly are the Hamiltonian potential, they are obstructions for doing this. So that's why tenfold day is able to detect them. But the information about these blue nodes is lost in this projection. So you lose any information about the possible braiding effects and so on. So if you want to correct for this, you have to do the spectral normalization differently. So what we do in our mathematical analysis is that we project the lowermost band to energy 1, the next band to energy 2, and the highest band to energy 3. Now, with this, the easy part of my talk is over, but I think that it really expresses the main essence of this non-Abelian topology. Now, in the remainder of my time, I will get more technical, but also more superficial. I will not really explain the details of all the arguments. I claim that this non-Abelian charge is in some way very unifying concept, which relates to all of these things which you see mentioned on the slide. Depending on how much time I have available, I will try to cover some of these. So first of all, it does generalize Berry phase. So tenfold way tells you that each band on this one-dimensional path carries a pi or 0 Berry phase, so there is some Z2 charge. So naively, you would expect that if you have n bands, each band can have Berry phase 0 versus pi, you would expect that there are 2 to n possibilities. It turns out that Berry phase is only able to distinguish 2 to n minus 1 of them because there is a constraint. The total Berry phase carried by all of the bands has to be 0 modulo 2 pi, so only n minus 1 of them is independent. On the other hand, if you do this generalized description, you find that there really are 2 to n possibilities. So for example, it is possible to have some one-dimensional loop on which each band has 0 Berry phase. Nevertheless, there is a topological obstruction which is associated with this 2 pi rotation of the eigenform. And I really present in the slides the discussion only for 3-band models. Of course, it generalizes to arbitrarily many models. So I will just flash here some mathematical description of the topological charge in this many-band case. So there are several mathematical statements. They are all actually simple, even though they look a bit scary. So first of all, whatever many bands you have, there is always this element which I call minus 1, which corresponds to the 2 pi rotation, so it's not trivial, but it squares to plus 1, there's a 4 pi rotation, and it's trivial. Second, each band gap is associated with some nodes, and they carry some charge g of j, where j is the index of the band gap, which is some pi rotation, and squaring that pi rotation gives you 2 pi rotations, so that's element minus 1. Then the most important one of all, if you have two band nodes with consecutive band gaps, so with indices j and j plus 1, their charge is always anti-commute. While if you have band nodes which are separated by a larger distance, their charge is commute trivial. So this is how you can describe it in more generality. So this topological charge goes beyond the Berry phase. Second thing that you can use it to is to explain the topological stability of nodal chains. What are nodal chains? So you know what are nodal lines. By nodal lines, I mean the occurrence of one-dimensional manifolds inside the momentum space, where two bands become degenerate. A nodal chain is the possibility of two intersecting nodal lines. And it has been known that these can be stabilized if you have some mirror symmetries. So I will not go to the details of this argument, but it turns out that in a two-band model, you can get a nodal chain very easily if you have a PT symmetry, some mirror symmetry with this Pauli Z matrix. Then if you write the most general two-band model, there is no sigma y because of the reality of the Hamiltonian. The mirror symmetry implies some symmetry on these functions hx and hc. And these sheets just show you that one of the functions vanishes on one sheet or the other sheet. So the red line indicates the nodal line which is formed with some simple model. Now, you might wonder, what stabilizes this intersection? Is there any topological charge? If so, how can you disentangle them? So for example, you might be wondering, how do you break apart nodal chain? How do you separate the horizontal part from the vertical part? And it turns out that this is not possible. If you break the mirror symmetry which is in this model, the nodal lines will always hybridize in this funny way that the vertical nodal line will sharply bend near the formal position of the intersection point, will sharply bend into this horizontal nodal line. And you will never be able to disentangle them trivially into the horizontal part and the vertical part. And the reason is that on this part which is there, which I call gamma, there is a 2-pi rotation of the eigenframe. And this charge is defined even in the absence of mirror symmetry. And because there is this 2-pi rotation, whatever hard you try, it will never be possible to separate the horizontal ring from the vertical one, because that would make gamma somehow contractible to a point, so, which is in contradiction with there being a topological abstraction. However, if we go to 3-band models, something funny happens. I have here some specific Hamiltonian with a tunable parameter E0. You see that if I take E0 to be negative, then the bottom 2 bands form these red nodal lines. So here is the spectrum along the high symmetry direction, and you see that this crossing of the bands corresponds to the nodal chain. However, when you keep increasing E0, what you find is that there will be a critical point. At some point, these two nodal lines separate. So what has happened? And you will get a hint of what is happening if you also plot into this diagram nodal lines formed by the upper 2 bands, which I show in blue. And you see that what really happens at the critical point is that you do disconnect nodal chain formed by the red nodal lines in one band gap, but at the cost of creating a nodal chain in the other band gap. So in some sense, there is still a topological abstraction around another axis in a different band gap. So in this way, the non-Abelian topological charge is able to explain the possibility, the stability, and the occurrence of nodal chains, and of their properties when you break symmetries of the system. So that was the entry here. Second thing, well, third thing actually, it turns out that this non-Abelian topology explains something called the monopole charge of nodal line rings. I didn't yet mention this. So what is a monopole charge? It turns out that if you study topological charges in this symmetry class, then you can define some topological charge on circles at the Berry phase, which is 1 → 0 versus pi. So the black nodal line ring will carry a Berry phase pi on this blue edged circle. But it turns out that if you do the topological analysis, then you will find that there is a Z2 charge defined also on these 2-dimensional spheres which enclose nodal line rings. This is called the monopole charge. It's also Z2 valued. It can be trivial or non-trivial. And what it tells you is whether the nodal line ring can be removed by shrinking. If the monopole charge is trivial, you can just shrink the nodal line ring to a point and then open a gap. While if the monopole charge is non-trivial, then you will see that you can at best shrink the nodal ring to a point, but you will never be able to open a gap. The only way how to get rid of a nodal line ring with the monopole charge is to annihilate a pair of them. So it turns out that one can use this non-Abelian topological charge to relate the monopole, the monopole charge in these spheres, which here is the stable limit and here are some fragile topological versions. You can relate it to the linking structure of the nodal line rings with nodal lines in the other band gaps. So for example, here I have 2 species of nodal lines, the blue ones and the red ones. You see that each blue ring is linked with 2 red links. So you will find that here the monopole charge of each of these nodal line rings is 2. So that's one of the things which you can do with this non-Abelian charge. Another thing, how am I doing with time? Okay. Another thing which you can do is to study something that we call node convergence. So naively you expect that if you have 2 Weyl of opposite chirality, plus and minus, and you bring them together, you would expect them to annihilate because they are kind of antiparticles of each other. And this really is what typically happens, but not always. It turns out that sometimes there can be additional obstructions. We noticed that previously in a work with Xiaoqi Sun and Xiaoqing Zhang. So the way this can be manifested is the following. Let's say that you have the C2T symmetry. I told you that in C2T symmetry you can have this non-Abelian topology as well. And this leads to some high symmetric plane inside the 3-dimensional momentum space. And it can stabilize Weyl points. You can have in-plane Weyl points which are kept to be inside of the plane because of the C2T symmetry. These Weyl points can carry positive or negative chirality, but inside the plane you can also calculate the frame rotation associated with them. And you can have the situation where two Weyl points of opposite chirality, both in plane, are approaching each other. So you would expect them to annihilate. However, you can take this spin path and calculate the total non-Abelian charge in this path. And if it turns out to be non-trivial, if it carries a 2-pi rotation, then whatever hard you try, even though the Weyl points have opposite chirality, they will not be able to annihilate. They will scatter. They will remain stuck inside the plane. If you have additional mirror symmetry in between, then it turns out that if you have the same obstruction in the C2T symmetric plane, then actually what happens is not just scattering. After the collision, these two point nodes will actually convert into another line ring which will be forming inside the high symmetric plane. And here I'm only discussing the possibility of two Weyl points with opposite chirality. One can get similar conversion rules for Weyl points with the same chirality, which are discussed in this paper with Shoucheng and Xiaoqi. So again, this is something which can be efficiently described by the non-Abelian topology, by the fact that there is this 2-pi rotation inside the plane. Going further, as I already mentioned in the introduction, you can do some non-trivial braiding inside the momentum space. So now you understand the colors. The colors were indicating the band gap in which the nodal lines, where the nodes are realized. So here you might have two nodes which are able to annihilate, and after the braiding you change the pi rotation to minus pi rotation, and afterwards they are not able to annihilate. So to demonstrate this phenomenon, we developed the model with Robert Jan and Adrien, which we hope might be implemented in some artificial systems such as cold atoms and photonics. It is a very simple system. You see that as a function of momentum it only involves nearest neighbor hopping on 3 orbitals, and as a function of time you only tune one onside potential here with this function f on the coupling between the other 2 orbitals, which are the functions h0 and h1. And as a function of time you would see that there are these braiding effects. Sometimes you collide Weyl points with non-trivial frame rotation charge so they scatter, while at some other times you collide them after the braiding such that they annihilate each other. So if you're interested in the model, this is like the most elementary model that we were able to develop where we discussed this possibility. Finally, you see I'm reaching conclusion. The non-Abelian topology says that there are some constraints on the possible nodal line compositions, that not all the nodal line configurations which you draw are possible. Some of them are intrinsically impossible. How do you get that? Okay, so you know this picture already from some other perspective. You see that I'm trying to assign some topological charge to this node here, the blue one. But I can either take this part on one side of the red node or the part on the other side of the red node. In one case you will get that there is a pi rotation, in the other case it's a minus pi rotation. So the plus pi versus minus pi can be used to assign orientation to nodal lines in 3 dimensions. So, but the rule is that because of the non-commutativity of the charge, that if nodal line of one color goes under nodal line of the other color, it has to switch orientation. So the plus versus minus pi rotation gives you orientation, but because of the non-commutativity of the rotations, going under nodal line of the other color implies that you have to switch orientation. So in this example, you will find that this example on the left is impossible, while this example on the right can be realized. And the reason is that on the left picture, it is not possible to consistently assign orientations to these 2 nodal rings, because as you go along them, you are supposed to flip the orientation once, which means it's inconsistent. While in this right picture, it's a more complicated picture, as you go along, you will find that you go on the nodal line of the other color even number of times, so it's perfectly consistent to assign orientations to these. Okay, I will flip this to save some time. The final thing that I will discuss is the relation to something called Euler class, the second Stiefel-Whitney class, which has been discussed recently by Bontun Yang and Ashwin Vishwanat's people. So the question is that if you have a many-band model, how do you effectively or efficiently predict whether 2 bands are able to annihilate each other when you bring them together or not? Because I showed you some simple 3-band examples, and 3-band models are easy to play with, but what if you have some DFT data where you have 60 bands? How do you tell whether 2 band nodes are going to annihilate or not? So to describe this, we developed an algorithm which calculates something which we call Euler class on a manifold with a boundary. So you take a region which contains the 2 nodes that you want to study, and which doesn't contain any band nodes inside the neighboring band gap. I will call it the domain D. And you will combine these 2 integrals, the surface integral of the Euler curvature and the boundary integral of something called Euler connection. and you will combine them. And it turns out that this combined thing is quantized to some integers, and it turns out that the two nodes are able to annihilate only if the value of this Euler class is 0. Now, this calculation is actually more complicated than it seems, because to make it work, you have to work in some special gauge. So playing with the gauge is a bit complicated. So such that you can set up the gauge already, I made a code available online where you can just put in your Hamiltonian with arbitrarily many bands, select the region, and you calculate this quantity. Now, just some more comments, because most of you are probably familiar with Berry curvature. It turns out that in these systems, Berry curvature vanishes identically because of the PT symmetry. The reality condition kills it. However, since this is a real vector bundle, there are basically some new geometric structures which one can define, and this is exactly the Euler curvature. So it's something like the refinement of Berry curvature to the reality condition. And then you can calculate this invariant, and it tells you whether two binomials can annihilate or not. With this, I am basically done. Just one more remark. Actually, it turns out that what I told you about the story of these frames describing eigencies of the Hamiltonian, it is mathematically isomorphic to a problem studied in the 70s, where people studied topological defects of something called biaxial nematic liquid crystals. In biaxial nematic liquid crystals, there are these molecules where the symmetry of the molecule is ellipsoid of where all the matrices are of different length. And it turns out that all the parameter space of this is the same as for the three-band Hamiltonians. So the topological defects, the declination lines, follow the same topological charge as the nodal lines in the Hamiltonians, which I told you about. I will skip this. And of course, there is a lot of open questions about the relevance of these two surface states, the transport, what happens in the presence of interactions. So I think that in the schedule there is some brainstorming session in the afternoon, so we can discuss some of these together if you want. With this, I'm finished. So I would like to thank my collaborators and all the funding agencies, and most importantly, I would like to thank you for your attention.